Hi everybody, welcome to the next video in the course. So in the last couple of videos we discussed something called marbles in a jar game, which showed to us that how chance plays an important role in that game itself, but then we built an analogy of the game with how evolutionary processes occur, and we saw how each marble jar could be looked at one generation, and subsequent jars is evolution taking place as we pass on from one generation to another. And we saw that natural selection is not sufficient to explain evolutionary processes, and that chance events also bring about evolutionary change. Smaller the population size, which was capital N, the greater the likelihood that chance is going to have a meaningful impact on evolutionary dynamics of a population. So small populations are at a greater risk of being dictated their evolutionary trajectory by chance as compared to natural selection. Large populations, on the other hand, are more dictated by natural selection as compared to chance events. Natural selection is able to act more effectively on larger populations. So what we will do in the next 2 or 3 videos is formalize this structure and develop some mathematical relationships in trying to understand these processes. As far as this entire course is concerned, the next 3 or 4 videos are going to be mathematically perhaps a bit challenging for those of you who are from life sciences background. But my honest suggestion to you would be to stick through these videos. We will take it very slow. We will try to develop the mathematics very slowly, and at the very least, even if the mathematical concepts prove inaccessible, we will discuss the geometry associated with the process that is going on. So even if you are not able to grasp the mathematical nitty-gritties, there are 2 things that I want you to take from these lectures. One is the geometrical intuition of the processes that we are talking about. We should have some intuition about what is the process that is being talked about in mathematical context, and it's okay if we don't get all of the mathematical nitty-gritties completely. The second is that whatever math we do, at the end of the derivation processes, we will derive some results. Those results have to be understood, if not mathematically, but in terms of their significance towards evolutionary processes. So we must realize that what does this result mean, and the results that we are going to derive in the next few videos are exceedingly important for our complete understanding of evolutionary processes. So with that background, let's start, and as I said, next few videos are going to be in this spirit that I just spoke about. So the broad question, we are going to be interested in 2 broad questions over the next few videos. The first one that I am interested in is the following, that if I have a chemostat whose volume is V, the flow rates are V naught, and if this chemostat is populated by individuals of a particular type. So at a given moment in time, all individuals in this chemostat are of this black genotype. So this is one particular genotype. Let's call it B type individuals. And at this time, what happens is that a blue individual comes in the population, and its fitness, this is a A type individual, which is carrying a mutation, and this mutation may cause a change in fitness or may not cause a change in fitness. So as far as fitness of this A type individual is concerned, we have 3 options, that fitness of A may be greater than fitness of B, fitness of A is equal to fitness of B, or fitness of A is less than fitness of P. This of course is a case where the mutation that happened was beneficial in nature. This is a case, the second one is a case where the mutation that happened was neutral in nature, and the third one is a case where it was a deleterious mutation that happened. We will not discuss the deleterious case, because in this case selection just takes care and eliminates this one mutant that has come up. So, this is not interesting, because this A type individual is less fit as compared to everybody else in the population, and selection is going to just remove it. So, we will not discuss this case. We will discuss these two cases where this is a neutral mutation or this is a beneficial mutation. So, this individual has arisen, and this individual could be one of the two types, either neutral or adaptive. The broad question we are interested in the, so I said we are going to ask these two questions that we are going to answer mathematically. The first question is, what is the probability that this system transitions from what is shown on the left to this state? So, the question of interest is, what is the probability that starting from only one individual of blue type, the system reaches the state where all cells are blue type. What is this probability? That is what we are interested in. In other words, this has a formal name, that what is the fixation probability of the blue mutant. And we are going to answer this question in two contexts. One, when the blue mutant is neutral as compared to the black genotype, and the other case where blue is adaptive as compared to black. So, I hope this question is clear to everyone, and that is what we are going to build on in the next few videos. So, before we do that, we want to understand an approach that we will be taking to answer this question. We need a mathematical approach to answer this question, and again you should realize that this probability of transitioning from this state to this state, this probability of transitioning is not equal to 1 even if blue is more fit as compared to the black genotype. And that is because, as we discussed last time, because since there is only one blue type individual, there is a finite probability that this blue individual is washed away from the reactor even before it has had a chance to divide. And once it has been washed away, then there is no more blue type individual left in the population, and hence the only possible state for the system is all black type individuals, and this probability of this transition is equal to 0. So, one assumption that we are going to make throughout this discussion when we are discussing this question is that no new mutations happen. We will discuss, once we are through with these derivations, we will discuss that how will relaxing these assumptions change our results, whether it will increase the probability that we calculate or decrease that probability, but we will discuss that at the end. But for now, we will assume that the blue and the black genotypes are the only ones that exist and no mutations happen. Blue gives rise to blue every time, black gives rise to black every single time, and that is it. So, before we begin to develop this framework, what we will do in this video is develop a mathematical process to analyze questions and systems such as this, and this technique is called Moran process. In a Moran process, from the context of our chemostat, the outstream let us say the state of the system is this, and we have some blue type individuals. So, we define the state of the system by a single variable, and that variable let us call it I, and I represents the number of blue type individuals in the population. We will also assume that since this is a chemostat and it always operates at a steady state, the total population size in this chemostat always remains constant at n. So, what these two immediately automatically imply that at this instant in time, number of B type individuals, which is blue, is I, and number of A type individuals, which is black, is simply n minus I. This is blue, this is black. Right. This is the state of the system. And of course, if I is equal to 0, then we are talking of a state where there are only black type individuals in the population. If I is equal to 1, then we are talking of this state where only one blue individual has come in the population, and so on and so forth. I equal to n means that it is only blue type individuals which are there in the population. So, if you think about the transition probability, the probability that we are interested in finding out, we are interested in finding out that what is the probability that the system transitions from I equal to 1 to I equal to n. Because this is a state where there are n blue type individuals, this is a state where there is only one blue type individuals, which is the start of the journey for the blue individuals, and we are interested in the system transitioning from I equal to 1 to I equal to n. That is our goal. So, in a Moran process, we will assume not 1 or n, we will assume that the system is at state I. I could be anything. Different values of I will represent different stages of the process. We will also assume that the fitness of the two genotypes is RB and RA. These could be equal in the case when they are both equally fit, or these could be unequal if the blue individual is fitter than the black individual, then RB would be greater than RA. Of course, we are not going to discuss the case where RB is less than RA, because as I said, selection will just get rid of the blue individuals that have come up in the population. Okay. So, in a Moran process, we are going to assume that since this is a chemostat, total population size always remains n. This condition is never violated. So, if at any instant of time I were to take a snapshot of this chemostat and count the number of individuals present in this chemostat, the number would be always equal to n. It never deviates. However, as you can see that this is a chemostat, so there are bacteria being continuously washed away from this chemostat, and there are new birth events continuously taking place in this chemostat. So, total population size is always equal to n, but this is in the face of bacteria being washed away and bacteria being born. So, what this means is that death, which is bacteria being washed away, is equal to birth, which is divisions taking place in the chemostat. These two have to exactly balance each other. So, in a Moran process, we are interested in that narrow sliver of time where one birth event happens and which is exactly matched by one death event. This is necessary so that the population size can remain at constant. If only birth took place, then the population size would go to n plus 1, in which case this would be violated, or if only death took place, then the population size would go to n minus 1, again that would be violated. So, the assumption here is that one birth, a new individual is born and one individual is washed away from the system at the same instant. So, the population size always remains constant. So, if this is the case, one birth and one death is taking place simultaneously, we have four options. We could have a case where an A individual is born and B individual dies or washed away. We have another case where B individual is born and A individual dies. We have two other cases, that an A individual is born and an A individual dies, and last case is that a B individual is born and a B individual dies. These are the only four options of one birth and one death event in the Moran process when I have only two genotypes in the population, and according to our definition, these are the only two genotypes. So, let us just note these here. B represents the blue type individuals whose fitness is RB and the state is I. So, B is blue individuals. The state of the system is I, that means there are I number of B type individuals and their fitness is RB, and the corresponding quantities for the black individuals is A is black individuals whose number is n minus I and whose fitness is RA. So, what we are going to do is that we are going to compute the probability associated with each one of these four processes. Let us start with this one. Let us start with the first one, and we are interested in probability that B is going to die, that the individual that is washed away from the reactor is going to be a B type individual. Now, if there are I individuals of B type from a total of n, the chance that a B type individual is going to get washed away is simply equal to I upon n, because in a chemostat, let me draw the chemostat here again. So, from the context of this death event, I have these individuals which are n minus I, and I have the blue individuals which are I. So, the probability of B dying is simply equal to I upon n, because the greater the I is, that means there are more number of B type individuals in the chemostat, the greater the chance that some individual, one of those I individuals happens to be here. If black is very large in number, that means n minus I is very high and consequently I is very small, then the chance that it is going to be a B type individual which gets washed away from the chemostat is going to be very small. Basically, what we are saying is that washing away is a completely random process. It could be any cell which happens to be close to the exit of the chemostat and then is washed away from the system. Hence, the probability of death of a B type individual is simply proportional to its numbers and equal to I by n. So, that gives me the probability of death. This has to be multiplied with the probability that an A type individual is born. This is computed, this is estimated with the following mathematical relationship. N minus I will write this first and then explain. N minus I divided by RA divided by N minus I times RA plus I times RB. So, this is the probability that an A individual is born. In the numerator we have total fitness of A individuals, which is fitness of each A individual multiplied with number of A individuals that exist in the population. In the denominator, we have total fitness of the entire population. So, what this means is that this ratio here is the fractional fitness of the entire population which lies with the A type individuals. If this number is very high, then there is a great chance that it is going to be an A type individual that is going to divide next, and if this number is low, then the chance that A type individual is going to divide next is going to be very small. So, this is again the chance that an A individual divides next is simply equal to total fitness of A individuals divided by total fitness of the entire population. This is just number of A type individuals times fitness of A individuals, and in the denominator is number of A type individuals times the fitness of A individuals plus number of B individuals times the fitness of B individuals. So, these two multiplied with each other ensure that they give me an expression for the probability that in the next instant in the reactor, a B type individual is going to die and an A type individual is going to be born. This is the probability that a B individual dies, and this is the probability that an A individual is born. And I hope that makes sense to everybody, but this is something that we are going to use quite often here on onwards. One more thing before we move forward with this is that if this happens, then what happens to the state of the system? Remember, the system was at state I, that means number of B type individuals was I. If this happens, if a B type individual dies and an A type individual is born, that means the number of B type individuals reduces by 1 because a B type individual died, and number of A type individual increases by 1 because an A type individual divided, hence their number went up by 1. So, the system transitioned from state I to I minus 1, where there were I number of B type individuals in the population prior to these two happening. Now, there are only I minus 1 number of individuals left in the population which are of B type. So, we are going to call this probability of transition from state I to state I plus 1, I minus 1, because we started when there were I number of B type individuals, and after these two happened, I am left with I minus 1 B type individuals in the population. So, I hope that makes sense to everybody. If this is clear, then the next three are going to take care of themselves and follow the same logic. So, let's do this. Let's do the next one. We get rid of this. So, the next is the opposite of this, that In this one, a B individual is born and an A individual is dying. What that means is if these two happen, number of B individuals increases by 1 because it's a B type individual that was born, and number of A type individuals decreases by 1 because that's the individual that dies. Hence, after these two are done, what we are computing is the probability that the system transitions from state I to I plus 1, because after these two happen, the number of B type individuals would have increased by 1, and that's equal to probability that a B individual is born times probability that a individual dies. We are going to use the same logic that we used in the above expression and compute the probability that an A individual is going to die, and that is simply going to be proportional to how many A individuals are there and how many B individuals are there. So, probability of A dying is simply proportional to how many A individuals are there in the population, which at this stage is n minus I divided by n. And you should see this is the exact formula what we wrote here, because this was a probability of B dying which was proportional to number of B type individuals, and now we are writing the probability that an A individual dies which is proportional to number of A type individuals at this point in time. On the other hand, the probability that a B type individual is going to be born is simply going to be equal to, using the same logic that we used in the previous expression, probability that a B type individual is going to be born is simply going to be the total fitness of B type individuals in the numerator divided by total fitness of the entire population in the denominator. So, the total fitness of B type individuals is number of B type individuals, which is I, times fitness of each B type individual, which is RB, divided by the total fitness of entire population, which is total fitness of B type individuals I times RB plus total fitness of A type individuals, which is n minus I times RA. And what you should note here is that the denominator in these two is exactly the same, the denominator in the death terms is exactly the same, only the numerator is changing depending on what probability are we calculating, which individual is going to die and which individual is going to survive. And this gives me the transition probability of system going from state I to state I plus 1. So, that is 2 out of the 4 calculated, and we will continue these calculations in the next video and develop this theme a little bit more.